So just a little heads up on what's happening. Tuesday, there will be a quiz. And then after the quiz, we're going to look at something I hope interesting. You find it interesting. It's something that they traditionally, and by traditionally I mean no more, they used to give at the very, very, very beginning of calculus. And then students hated it and they didn't really understand it back then. And I always thought, oh, it's important, but it'd be useful at the end. Take a look at it. So we'll do that, and hopefully that'll be interesting. Then Thursday, I'll try and get the review sheet to you Tuesday. I may be a little pressed for time with the quiz and everything else. But I'll certainly get you a review sheet by Thursday, and we'll go over it. And you are encouraged to review past quizzes, homework, and bring questions, because it's just me here going, you need to know this and this and this. Is going to take 10 minutes. Today, I think the stuff we're going to do today is really interesting too. We'll get to that. Okay, are there any questions on the homework? Do some homework. Okay. Yeah.
Give me a second. It was either 7 or 8.
I'm not sure either.
It's page 514 though. 36. Oh.
Solve the differential equation.
Right. 8.
8. Okay, so these are all in the section on separable equations, right? I wonder if the purpose of changing the variable names is, try and confuse students, or just try and show them that not everything has to be X and Y. Okay, that's the one. Okay. So we want to get all the Y's on one side and the thetas on the other. So that's not too hard. So on the left we have what? Sine squared theta on the bottom, secant theta on the top, and d theta. And then we have e to the y over y. Wait a minute. I'm not getting a good start here, am I? Put the y's over on the left. Y, e to the y, dy. And sine squared theta over secant theta, e theta. Those look terrible. Maybe if I rewrite it this way, y e to the minus y, that looks a little better. Anything I can do over here? Secant is 1 over cosine. It's like tangent times.
So it's cosine.
Oh, right there. I'm thinking that See, I'm thinking, I'm just trying to guess ahead, how am I going to do this? I'm thinking, well, if this was sine over cosine, right? So that's, derivative of cosine over cosine, so like maybe 1 over cosine squared, right? Since that's the tangent, whatever. But it's sine squared, so I probably...
What would be sine squared cosine, right? Because that's, or not.
Oh! Sine squared cosine. That's what you mean?
Yeah.
Yeah. Okay. This clearly, you should look at this by now, and you should... Oh, I love the way, what's his name? This French professor would say, well, it smells like integration by parts. So we say u equals y, and v prime equals e to the minus y, and u prime equals 1, and v is equal to negative e to the negative y. So this, since I have all this board space, I'm just going to take it up. Integral y e to the minus y dy equals y, negative y e to the minus y, numbers like that, minus the integral of this, which is just plus e to the minus y. What's that? So minus y e to the minus y minus e to the minus y. Okay, that's the left side. And then this looks like sine cube theta over 3. So we have, is that right? Yeah. So we have negative, let's take out negative e to the minus y times y plus 1 equals sine cube theta over 3, or we could put 3 here. And we're not going to be able to solve for y, are we? Not very easily. So that's just an implicit solution. And that's all you can do. But if I said, plus c, all right? If I said something like, well, what if, I'll just make something up. What if I said y of 0 equals 0? So you plug that in, you get minus 3 times 1 equals 0 plus c. So you'd say c equals minus 3. So, you do this. Then, if you wanted to graph it, you could start plugging in y values and solve for theta. That would work. Is that clear now? I mean, that stuff fun. Up here. Okay, any other homework questions? Okay. Just get. No, I didn't get everybody. Okay. So the end of Tuesday, I kind of fell into a hole, and I wasn't really planning to go down the hole. I was just planning to show something interesting. So I went home and I looked at, well, what did I do wrong? So wow, this is really interesting. But I'm not sure if we're gonna make it to where it's like, wow, that's incredible. Mathematics is cool. But I'm going to try, because I really think there's something really cool here. So we were looking, I'm going to write it, I have it in my notes in the terrible, it's not terrible notation, but I'll just write it like this. So a to the n y, I don't know, let's just give an example. A4y fourth derivative plus a3 y third derivative plus a2 second derivative plus y second derivative plus a1 y derivative plus a0 y equals 0. This is just an example of a fourth order linear differential equation. Technically, this is homogeneous. Actually, I don't really need to explain what that is. It's a homogeneous equation. And we talked about the fact that there's a polynomial associated with this. A to the fourth, r to the fourth, a3, r cubed, a2, r squared, a1, r plus a naught equals 0. And since that's a fourth degree polynomial, it's going to have roots. r1, r2, r3, r4. And so each of these represents a possible solution, y equals e to the rix. And there are 4 of those. But the question I was trying to examine at the end of Tuesday was, well, wait a minute. What happens if, say, R1 is equal to R2? They're all the same. Well, this is just one solution, but I was trying to suggest in that case, if we have R1 equal to R2, another solution might be xe to the R1x. So let's at least examine an example of that, right? See if that seems plausible. I'm going to run out of board space sooner or later here. So let's take a real simple example. See how it pans out. So we're just going to look at y double prime minus 2y prime plus y equals 0. And our polynomial is r squared minus 2r plus r equals 0. So we factor, we get r minus 1 times r minus 1. So we know that...
Is it plus r or plus 1? For r squared minus 2r plus 1?
Oh, 1. Sorry. Thank you. Keep me honest. Thank you. Yes.
Okay.
Yeah. So we know that Rx is a solution. And the question is why x Rx, is that a solution? Oh, R is 1, right? So we don't need an R. So let's check that out. So y is x e to the x. Y prime equals, okay, x times the derivative e to the x plus e to the x times the derivative of x. That's y prime. Y double prime is, well, the derivative of this is this. The derivative of this is e to the x. So it's just 2 e to the x's. Right? Now we want to check this solution. So we have x e to the x plus 2 e to the x minus 2 times this, x e to the x plus e to the x plus y. And we want that to equal 0. So we have x e to the x plus 2 e to the x minus 2x e to the x minus 2 e to the x plus x e to the x. So we've got minus 2 of these, one here, they cancel. We got 2 of these and minus 2 of these. So in fact, this is a solution. Okay, this suggests something really deep and beautiful about the solutions to linear homogeneous differential equations. But before I explain what that is, we have to go back a little, do a little review back from the Math1b class, the pre-calculus. And I'm gonna digress for a minute. You should all find this really straightforward. I want to talk about vectors for a second. Now, in Math1b, we talked about vectors, but what we really mean is 3D Euclidean vectors. What's a 3D or 2D? We'll talk about 2D. How about that? You've got a nice flat board here. So a vector is just a directed line segment. There are 2 points, and it has a direction, which we usually represent as an angle, and it has a magnitude. And we'll typically write a vector, this is like V, as a letter, often V or U, a little arrow under it. It's not a scalar, it's not just a number, it has direction. We have some important properties of vectors. I think I'm going to write these over here because I don't want to keep them. So if we have vector 1 and vector 2 vectors, then vector 1 plus vector 2 is a vector. What do we mean by adding 2 vectors? Well, we want to add V and U. We put the tail of U at the head of V, like this. And the new vector, U plus V, is this vector that goes from the tail of V to U. Is this familiar to everybody? Should be. Part of that class. Okay. We also have the fact that we have some constant like A, remember the reals, and some vector. Then we can multiply that constant times vector, and we get another vector. Again, we have a vector V, let's say, and we want to multiply it by 2. That's just, we just multiply the length of V times 2. It's a notation for the magnitude of V, or the norm of V. Right? So that's the second property of vectors. And finally, you could have overlooked this. There's always a special vector, which we write this way, the zero vector. And it has the property, if you have a vector, then the zero vector plus that vector is just that vector. This might remind you of some properties of real numbers that you've run into in the past. Okay, so when you have these three properties, in mathematics we call this we call it a vector space. A vector space is all the vectors, member of the vector space, and these that follow these properties. Now, given that there's a few interesting properties you should know about. This may be a little new, some of this. When we were doing 3D vectors, we defined vectors I, J, and K. Does anyone remember what these are?
Are they on the XYZ axis?
They're in the XYZ direction, yes.
Okay.
And what do we know about their magnitude?
1.
It's 1. So these are 3 unit vectors. And I'm just going to very loosely say their directions are different. That's pretty imprecise, and actually it doesn't, I mean, you could have I this way and J this way, and K over here, and that doesn't, on the board flat, and that doesn't really say at all, K has to kind of stick out. But in any case, these happen to be orthogonal. So you know what orthogonal means? Anyone not know what orthogonal means? Oh, it means perpendicular.
Oh, okay.
That's all. It's just a synonym.
Just say perpendicular.
I don't know. What can I say? I don't know why. Strangest things come into your head. When I was 16, I was in a math class over the summer, and we had some visiting lecturer, and I worked for the ortho company, and does anyone know what they make? And one of the women's in the audience says, "Well, is it fertilizer?" And the guy goes, "Well, close. It's birth control, but ortho." Okay. One of the properties of a vector space is if you have 3 vectors like this, or for 3D Euclidean vector space, is that any vector can be made up of what we call a linear combination of these vectors. Right? Any vector in 3D Euclidean space, you take I, J, and K, and you can combine them in such a way that you get that vector. This is a property of all vector spaces. That is, there's a minimal set, right? In this case, I, J, and K, for which you can generate every vector. And this is not a unique set. For example, I could say 2i, 2j, and 2k. And these don't even have to necessarily be in the same direction. They can't all, they can't be what we call be a linear combination of each other, but it's not unique. And there's a name for this set, and it's called, and this is, I'm sure, I hope, new to you, it's called a basis. Has anybody heard of a basis before? It's not it sounds new, so it sounds foreign, but just think, we just take three vectors that you can do this. You could think of them as I, j, and k, the unit vectors, but they don't have to be. But there's some important properties about the basis of a vector space that I want to mention, right? Which is the size of this set is always the same for a vector space. So for this 3D Euclidean vector space, of course, the size is 3. And we give that a name, that's called the dimension. That's the dimension of the vector space. How many vectors it takes to make up this basis. Okay, that's the background. I hope that's clear. Why did I take this very wild and obscure direction here? Well, I guess I want to. I'll leave that here. I want to go back to this example up here, right? So we found that for this differential equation of order 2, that we have two solutions, y equals e to the x and y equals x e to the x. And I wanted to make clear that for a differential equation, if you have this kind of differential equation, if you have a solution, that there are things you can do with those solutions. For example, let's say, we'll start with this. If this is a solution, what about y equals some constant, let's say b e to the x? Well, looking at the original differential equation, right, we know that y prime equals bx dx plus b e to the x. Y double prime equals bx e to the x plus 2b e to the x. And if we plug this in the way we did up here, then b is just going to be a constant in each of these terms, and you can just divide it out. So this will always be a solution. Likewise, you could pick some other constant, some arbitrary constant, and for every value of c, this will be a solution. And in fact, you could combine these. This will be a solution. I want this to remind you a little bit of the fact that a vector can be made up of this basis. Linear combination of these solutions is a solution. A linear combination of these vectors is a vector. So I guess the next big leap is to realize that in mathematics, a vector space has vectors, but they're not necessarily these Euclidean vectors. They could be some other object. And in fact, they could be a solution to a differential equation. Right? So let's look at that a little closer here. Let's look at solutions just to this differential equation for a second. If we have two of them, their sum is a solution. If we pick some constant, some real, we can multiply that by the solution, we get a solution. Oh, what about this? We need a zero vector. Well, what about y equals 0? Y equals 0, y prime is 0, y double prime is 0, and 0 minus 2, 0 plus 0 is equal to 0. This is also a solution. We have the third property. So what we're getting here is that solutions, I'm just going to write this down, solutions to linear differential equations form a vector space. Now, let me just ask a question about that differential equation. What's the dimensionality of that vector space? The y double prime minus y prime plus y equals 0. What's the dimensionality of it? Well, how many members would we need to form a basis? Well, I think we know that. Use e to the x and x e to the x. So the dimensionality is 2. Coincidentally, the order of the differential equation is 2. Is anybody seriously lost at this point? Because I'm getting that feeling. This is very abstract. I'm not expecting you to kind of take the full weight of this in. But there are seriously good things about the fact that we can say this. Study of vector spaces is very extensive. Once you finish calculus, or even after this class, you might take a course in a subject called linear algebra. And if you ask a professor what's linear algebra about, and he doesn't really think very much of you, he'll tell you, well, we're going to study matrices. But if he does think something of you, he's going to say, well, it's the study of vector spaces and their transformations. So, okay, let's kind of round this up. Let's make this as concrete as I can make this. So, a linear differential equation of order n, to be very general here, has an associated polynomial. For example, here, the associated polynomial is just clearly r squared minus 2r plus 1. All right? if R is a root, I guess a singular, a unique root of this polynomial, then y equals e to the rx is a solution. If R is, I guess we're going to say, has multiplicity m, then y equals e to the r, y equals e to the equals x e to the r, y equals x squared e to the r, all the way up to y equals x to the m minus 1 e to the r x are solutions. And finally, these solutions form a vector space. So the takeaway is you have one of these equations, you solve a polynomial, and you have a solution to a differential equation. So it's actually a very, very simple, straightforward process. It's just, I'm going to do the first example for you on this handout. So we're going to look at this differential equation. And the first question is, the hard question, what's the dimensionality of the vector space formed by the solutions? It's actually very easy.
2.
It's just 2. That's right. So we expect to find 2 solutions, right? So what's the associated polynomial?
R squared plus 4r plus 4 equals 0.
Okay. What are the roots to this? This is r plus 2 times r plus 2 equals 0. So the roots are minus 2, but with multiplicity 2. Okay? So the solutions are y equals e to the minus 2x, and y equals x minus 2x. And the most general form would be y equals a e to the minus 2x plus b x e to the minus 2x. That's all there is to it. Okay, I'm going to give you this handout, and problem number 2 is a little harder. You have your fellow classmates with resources too. Did I skip you?
No.
No. Okay, anyone still working on the problem? Okay. Does any brave soul want to take a shot at this?
So number 1 and number 2.
Well, we just did number 1 on the board. So this is for number 2. Is anyone not familiar with Pascal's triangle? Really useful tool at times.
And then from here on, I'm pretty much guessing.
There's no guessing. From there on, you solve the problems.
Yeah. Oops. Oh yeah, and the way you get this polynomial is that you need to make sure that this is negative, so this -1 cubed does equal -1. So it's pretty convenient.
It was very nice to handle. I hope everybody is kind of on top of this, what he did. I guess the trickiest part might be factoring a polynomial like that. Obviously, it's designed to give you a nice, easy result. You recognize what it is. Those of you who are just too polite, you take expression like this and you factor it out, next to the n plus n, next to the n minus 1, whatever, all the way to 1, right? You want to know what the coefficients are here. You can always use Pascal's triangle. Just come down here to n and you'll see what they are. There's also a connection here. These coefficients are to combinatorics. If you're familiar with the C notation, this would be C1, CN1, CN2, and so forth down to CNN. C meaning how many combinations of, I guess this would be C0. How many combinations of 0 items are there in N, and so forth. So you should be familiar with this, I hope. Okay, why don't we take a break? Come back and we're going to do a little different topic. That'll probably finish off the serious stuff of the class. Maybe you don't want to go outside. It's nice and cool in here. Hi.
All I saw was that.
He's already here.
That's going to be hard.
I know. That's a challenge for you.
It's always possible that there's a way to do it directly. I would suspect you'd have to use some kind of numerical method, like Euler's method.
Yeah.
Did you get that problem from the book?
No, I
Just made it up? Oh, okay, good. Well, think for a second. So, second derivative, sine. Well, first thing that would help if you're going to use a numerical method would be a starting point, right?
No, and I figured out a way how to simplify Euler's method a bit.
Okay.
Yeah.
Are you going to make that part of your project that you're going to get extra credit for?
Yeah, I already.
Okay.
I just
cool.
need to write up the code. I already did the formulas.
Well, I think it's pretty clear that that's going to work as a starting point, right? Oh, we're not going to be able to use Euler's method, are we? we only learned how to use Euler's method on a
First order?
first order. Might have to take out the big guns. Well, let's see. You know, there's something you can say about this for very small y. Which is sine of y prime is approximately equal to y prime for y prime, small. So as an approximation, you could solve it, the way we've been solving these, which would be the solution, write it this way, y total prime equals y prime over pi plus y over pi equals 0. So the equation would be this is the quadratic formula, right? 1 over pi squared minus 4 over pi all over 2. Again, this is just going to be an approximation for very small y. And this is like this is a imaginary, right? So the solution, I have to look it up, but it's going to be periodic in it for a short period. It's going to have a sine and a cosine in it. So probably something like y equals e to some as yet unknown e, probably like sine of some unknown factor. Okay, so this is going to be, for very small y, this is going to look like the sine function solution that starts at 0. And after that, I have no idea. I'm trying to think if there's anything run into that would even have that complexity. A very, very simple model for a star is you have, this is like a little piece of shell, here. You have gas, it's pushing out, it has a pressure, and you have gas pushing in, it's has a pressure, and there's a little difference, there's kind of a delta P, and you also have the force of gravity on the mass outside, so that, all this, area times gravity, well, the pressure of gravity, right? Because this is a steady state, those have to match. And there's a lot of complexity there because pressure in a star, the outer part of the star is just like a regular gas, but as you get further in, it's ionized. It's all this stuff. But you still, you have a relatively simple differential equation describing this. Where it gets complex is that you have a very large star, red giant, right? Extends way out here. The gas is very, it's not as dense. And the transport mechanism for energy leaving, like in this case, it's typically just radiative or
Light, radiation.
radiation or what's the word? How do you move energy? Radiation.
Energies move through radiation.
Convection, conduction. So in a small star, it's conduction and radiation. But out here, you get convection, which means that you kind of get these bubbles that rise and fall. And I'm thinking, it's probably like a periodic function. So you might actually, you have to get pretty sophisticated to run into a problem like this. And again, you wouldn't try and solve it. If you're an astronomer, you wouldn't try and solve this in closed form. Normally, you use a computer and generate a model, and then you compare it with how it actually worked. But anyway, that's just applications. Mathematicians aren't interested in applications. Fortunately, I'm not just a mathematician. So. Okay. Now, are there any other questions about this last topic? Hope you'll all go on and take linear algebra. I don't think they'll mention differential equations in a linear algebra class. In the differential equations class, they might mention linear algebra because it'll come in handy. So we're going to find one more fun, useful purpose to differential equations today, this quarter, this school year, I guess. School year end in the summer, I guess. Used to. Yeah, quarters is just kind of go on endlessly. You pick any starting.
Actually, there's like a summer quarter that started like just this Monday.
Yeah, but like let's say you applied to Foothill. Could you make the summer quarter your first quarter?
Yeah. Yeah.
So it's just like a revolving door. You just get on whenever you want.
Well, I mean, at Foothill,
The ride
there's
never
one that
ends.
started Monday.
Sorry?
At Foothill, there's a summer quarter that started Monday.
There's about 2 summer quarters.
It's weird.
It is.
I guess it's like the early bird.
It's great if you don't want to have a life, I guess.
You say that like you think that's a bad thing.
Well, it's an opportunity cost.
It's funny because I just, on the way in, I was listening to the radio, and what's this guy's name? The actor who plays Geordie. Lamar Alexander, is that his name? He was like saying, kids should learn to read. They should learn to read. It's fun. It's great. And then they had a teacher on who said, yeah, but they should take the summer off and have fun. It's kind of the same issue. Okay. As I said, we're going to talk about one more subject, which is called, get it.
Orthogonal trajectories.
It's called orthogonal. And now you know what orthogonal means. Okay, I'll just say perpendicular. The thing is, everything that's perpendicular is orthogonal.
But not everything that's orthogonal.
Yeah, orthogonal is a little general, more general concept. If you had like 2 vectors, right? And you take their dot product, right? And, oh, I'm going to do that wrong, aren't I? Is it the cross product or the dot product? Yeah, if you take the dot product and it's 0, right? You know, then these are perpendicular. So if you take the idea of a vector space where you don't have things that point, you can still have vectors which are orthogonal because they obey this, but they're not perpendicular in the geometric sense. Oh, there's a really wonderful example. Digressions.
Things
You're
orthogonal.
going to get done early today. You're going to get off from class early today anyways. So if you take sound, you know, like if you ever watch a scope, right?
Oscilloscope,
Oscilloscope.
good enough.
And you'll get a repeating thing that'll change, right? But, you know. So turns out there's a whole topic in mathematics called Fourier analysis. And the basic idea is that this wave form can be made up of a bunch of sine waves. That's one of them.
With different amplitudes and phases.
Well, I'm going to leave the phases out for the moment. And then so those of you who are musicians, are any pianists here? Anyone ever played piano? Now, these are octaves. Right? You cut the frequency in half and you get the next octave up. And you combine these with the right coefficients, these sine waves, and you can get anything you want. But the question is, how do you, going from this, find out these coefficients? And it turns out that these vectors, that's what they are, these vectors are orthogonal. They're not perpendicular, they're orthogonal.
To what you're looking for?
That is, if you were to integrate, say, from negative pi to pi, the sine of theta and the sine of 2 theta, you would find that that is, we'll just say n theta and m theta. You would find that this is either, forget what it is when they're equal, but if n equals m, we'll just say it's 1, but if n is not equal to m, they're orthogonal, it's equal to 0. And that's really useful because you apply this integration to your waveform multiplied by one of these, and you just get that component out. So thank you. That's a really great example of orthogonal, but not perpendicular. But if you said perpendicular, I think the mathematician would know what you're talking about. Well, this is all very abstract. Let's go back to pictures on a blackboard. Erase that. So, definition of an orthogonal trajectory is, it's a family of curves. Writing's just getting terrible. Which is perpendicular at every intersection of another family of curves. Okay, so we want some simple examples so we can understand what the heck this means. So for my first trivial example, my family of curves is y equals a, where a is a real number. I'll draw a picture of that. So graph and family of curves. All the ones in between. So my orthogonal trajectory would be x equals some other member of the reals. Just
Yeah.
right? They're everywhere these things cross, perpendicular. Such a simple example, you might wonder, could there be anything more complicated that would fulfill this?
Circles.
Yeah, well, some people like to cheat look at the book. All right, maybe not. So, if you were to take circles with origin, in other words, x squared plus y squared equals, we'll say r squared to be nice. If you take the family of circles, by the way, I think it should be obvious that the particular family you're talking about, you can switch. If you have an orthogonal trajectory O, which is perpendicular to P, and P is an orthogonal trajectory to O, right? It's kind of a symmetric definition. So, okay, so what are the orthogonal trajectories of these circles? Well, they're just any line goes to the origin, right? That's really fundamental geometry, right? The radius is always perpendicular to the circle. But it turns out that there are many more interesting examples. Let's take a look. Okay, and this is really a nice application for what we've just been learning, differential equations. So we're going to look at the family which is x equals some constant times y squared. And first we want to at least take a look. What is that? What does that look like? What does one of those numbers look like? You know?
Parabola.
They're parabolas. They're sideways parabolas.
Oh.
Right? Instead of y equals x squared, they're x equal y squared. And because k can be positive or negative, they can go in both directions. And they all go through the origin. I suppose you could do something like we did with those direction fields with this. You could start yourself someplace and kind of draw perpendiculars, and you could try and kind of figure out what this thing is, but we're gonna use a more direct route. So first we're going to do some implicit differentiation here. Everyone recall implicit differentiation? Just going to find the derivative on both sides where y is a function of x, right? Implicitly. So the derivative of x is 1. The derivative of y squared, ky squared, is k times 2y times dy dx. Okay, there's our derivative. We want that. Anyone think about why we're going to want that? Why we're going to want the slope of the curve here, right? At each point, I guess you need a different color. Why do we want the slope at each point?
Because the inverse of it is going to be the perpendicular line.
The negative reciprocal of it.
Negative, yeah, exactly. I knew what you were thinking. I made that mistake. Okay, so we can solve for this. dy dx equals 1 over 2ky. But it would be good if we can get rid of this k. Which of course we can. We have an equation with k, and we can see that k is x over y squared. This becomes y squared over x times 1 over 2y. So it's just y over 2x. All right. That's our derivative at every point on this in terms of x and y. So we want a family of functions that is always perpendicular. So we want a family of functions whose derivative is just the negative reciprocal. Wow, that was too easy. We have a differential equation now that describes whatever the orthogonal trajectory of this is. And all we have to do is solve this. Okay, how are we going to solve this?
Put 1 on one side.
Yeah, this is a separation of variables. Okay. So we have y dy equals minus 2x dx. Integrate both sides. Y squared over 2 is negative x squared plus some constant. Or, if you like, y squared over 2. And I'm going to see how many of you are really sharp. Square root of 2 squared plus x squared over 1 squared equals c. Oh, actually, I want to divide by c. Okay, what's that?
It's an ellipse.
This.
Is it an ellipse?
So for each, this is a family, right? It's going to run through different values of c. But for each c, this is an ellipse. Its major axis is along what? Along the y. And its minor axis is along the x. And remember the formula for the eccentricity? It's going to be the same for all of them. You remember what the eccentricity of an ellipse is? That you can kind of have an ellipse that's almost a circle, right? Or you can have an ellipse that's kind of like this, you know, orbit of the Earth, orbit of a comet, right? So the eccentricities of all these are the same. So we, again, risk embarrassing my artistic abilities. So we're going to get a bunch of ellipses. I don't know, I had fun doing that, and maybe you'll have fun doing this. For those of you with unbounded curiosity, I ran into something like this before, and I really can't remember. You can Google it if you want. I think it's a topic in topology. It's called conformal mapping. And the idea is you take something like this is supposed to be a frog, don't laugh. It's gonna have big legs, right? And there's kind of a grid here, right? And you do a transformation on this, like this will make the legs. Now the head is kind of big and the body is kind of small. And you do this mapping in such a way that these grid lines maintain the angle. All these angles get inverted. I don't really know anything else about it, but it was interesting at the time. So, all right. I mean, clearly a use of this idea. All right, you have your handouts. On the back, there are two orthogonal trajectory problems. Why don't you work on those, and we'll take a look at that. And then we'll leave early so we can get to the beach before the sun goes down, okay? Oh, homework. Thank you. I already have homework. I have to write a quiz for thanks anyway. Okay, that's a good question. I'll give you a good answer in just a second. I think it's just 7-1, 7-2, not everything necessarily. We're not doing mixing problems in this class. 7-3.
Wait, what's 7-2? Because for the homework, I thought we had like a 7.1 and then 7.3.
7-2 is direction fields and Euler's method. Seven three, separable equations and orthogonal trajectories. And if you learned anything about solving linear differential equations, that might come in handy. That's not actually in the book. That's in my notes, if you want to look up the video. Didn't you do that already?
No.
No. I'll look at it. I'm not looking. Can I touch it?
No.
Can I take it home with me?
Yes.
Jeez.
You can burn it.
Well, hopefully
What?
we'll all, in the end, recycle it, right? Politically correct thing to do?
It's too hot to burn things.
Recycle, I didn't say burn.
Yeah.
Freeze it.
Freeze it,
You
yeah.
wanna,
Make it all
Why not bump it?
reverse burn.
Like a tray, put it in there, put some water on it, sip it.
Yeah, yeah.
conformal mapping, also called a conformal map, conformal transformation, angle preserving transformation, or biholomorphic map is a transformation that preserves local angles.
Say that 5 times fast.
It's interesting to think you can just take any old image and kind of distort it, but all the, like any lines that crossed before have the same angle.
So does it have to be perpendicular then, or can it
No,
use that?
no.
Ah,
No, in other words, you could like you might have an informal map like this, and then you transform it, you know, somehow, and now, right? But it's not just these lines, it's every line would have to stay the same. What's it good for? Oh. Damn it. I know the answer. I didn't mention this in this class, but in the trig class I mentioned it. And I got this look of disdain. Oh. So again, I will risk embarrassing myself, and let's see. There's like North America, and then like that's Brazil. And then I don't know, some England out here, whatever, Greenland, and then there's like Antarctica here. So there's a map. It's called Mercator projection. Everyone familiar with this? Like when you went to grammar school, there was it's supposedly, there's Africa. Africa's over there, and then there's Australia. So this I didn't complete Europe, that's okay. You know, I don't know. It's over here somewhere. There's Japan, right? Whatever.
Oh, no.
This is accurate.
Malaysia, whatever. So this map is supposedly responsible for people having a distorted view of the world, because in this projection, like Greenland is as big as South America, right? So you might say, so what's it good for? Well, Mercator projection maps were made for sailors, right? So the idea is that, you know, you're out here in the middle of the Atlantic and you're trying to go somewhere, and you draw a straight line on this Mercator projection, and the distances are hokey, right? Distance doesn't tell you how far something is. But a straight line on here is a straight line on the globe. So it's kind of a conformal map. It also has this weird property that you never see the north or south pole on here. Do you know why?
It's the entire bottom and top edge. The entire bottom or top edge.
No. I used to think that.
Neat.
It's worse. It's much worse than that.
Oh, they don't even include that part?
They're at infinity. The mapping from the regular latitude to the one on here is the tangent function. Right?
Oh.
So what happens to the tangent at pi over 2? That's where the North Pole and the South are negative. It's North and South Pole, they're at infinity. It's funny because you think, well, they're almost there. How far could infinity be?
We broke the.
Yeah, so that's conformal maps are good for something.
Hey.
New cats.
potentially work sometimes.
Yeah.
How did I?
So, okay. Anyone, you guys had enough time for these? Yes, I guess. All right. And Daniel, please take this as a compliment.
Hmm?
Is there anybody other than Daniel who wants to try number 3?
Good, because I don't think I did it right anyways.
Anyone want to take a stab at it? Any brave soul?
Why not?
Can you tell me whether my answer is right and then I'll go?
You have to be brave in mathematics.
But she's nervous.
Would you rather do 3 or 4?
I don't want to do any now.
I can do
Think of this as you know, like opportunity to test your public speaking ability, right? Like everybody needs that in the future, right? Like I could never do it. I just get up in front and make a fool of myself all the time. What?
Can you look at it first?
It's okay to make a mistake.
He will walk you through it.
I'll help you out. If you make a mistake, I'll help you. Okay? Are you gonna do 3?
Yeah, I guess.
Okay.
If I didn't do 3 right, I didn't do 4 right either.
Well, 4 has less exponents, right? I'm just thinking of something.
You got it wrong already.
What?
I'm not looking at you. Just don't. I was thinking, if you happen to have a Mac, there's probably something like this for a PC, but if you happen to have a Mac, all Macs come with a neat little program called Graph Assistant. It doesn't, you'd have to look for it. Come on. And I was just thinking we could,
I did it wrong?
No, you did it good. Okay. Keep
in
going.
front of you. See, you do have to like learn to deal with hecklers.
What is your necklace?
Where you keep it up.
So you did the implicit differentiation. That was very good. You solved it. That looks fine. Good. Don't be afraid. So if I said y equals square root of x cubed.
It works.
Okay.
Yeah.
So how do I add one? No, I don't want a new one of those. I want a new one of these. How do I?
Right.
How can I do this?
Function new. Yeah.
I want to do equation.
Wait, yeah, right click on that.
Equation, new
Right
equation.
click is 2 fingers.
Yeah.
So
Yes.
negative square root of x cubed. Okay, and then we really want to square root negative x cubed, because k can be negative, right? And then we want equals negative square root so these guys look a little like a parabola, and then all of them are going to go through 0, so they're just going to be more of them. Right? Okay, how are you doing over here?
Not sure.
Okay, so, you replace K, yeah, okay, good. And then, so, let's see what happened, the X did that. Oh, yeah, okay, so what's that?
Oh, there's an arrow drawn to the other side.
Yeah,
I think I did it
oh,
right. Not
Oh.
sure.
and then, is this what came out of it?
Yeah, I'm not sure if it's, I'm not sure what the final end, how you're supposed to put
Well,
the
what is that? What did you come up with? What is that thing?
I don't know, that's what it said in the book.
It's another ellipse, right? Can you see my arrow here? Well, let's just try and graph one, right? Equation, new equation. So again, we have to do this trick where we just let's use C1, right? So let's say y equals 1 minus x squared times 2/3, right? So y equals, oh wait, the square root of. I don't know, can you do this on your graphing calculator? No. Here we go. See the ellipse?
Yeah.
I mean, I didn't do the bottom of it, but a little more efficient here.
Equation. No, that's examples. Equations is,
Oh,
yes.
Thank
yeah,
you.
Indeed. There's a y equals. Me one
That's
y.
not the right one.
Only one of the y equals.
Yeah. Oh, I see.
Now,
Here we go.
Oh my goodness.
Very good, Catherine. You got the right answer. Okay. Some other brave person? Or Daniel? Okay. Gotta do
I'm gonna do it. I'm gonna do it on the fly. Whatever.
The homework for tonight is just 2 of these problems. So by Tuesday, you should be good at doing, right? Okay, what's that?
It's like a,
Pergola?
It's a hyperbola, yes. Yeah. Everyone remember hyperbolas? They're kind of like if you had an ellipse and you, nah, that's not true. Kind of go off. This, and then look at the major and minor axes. They become asymptotes to the curve. So there's again, for whatever that curve was, y equals
Which is the
k
reciprocal
over x.
function? Reciprocal function?
Reciprocal, yeah.
Yay.
These are, there's some family here of these that is always perpendicular to it. I think I got something to say before we're done. Turn the camera back. Let me think out loud for just a second. So we're pretty much done with the material you're going to need for this class. Like I said, we'll look at something a little mathematical after the quiz. I'll be here for a while if you have questions.
I have a question. What's going to be on the quiz?
What did we say, section 7, 1, 2, and 3, was it?
Yeah.
Yeah.
What is it?
Tuesday. Tuesday. What do you think I'm saying? It's funny, I feel like in some ways I learned probably more than some of you guys here. Not about math, you know most of that already, but I enjoyed this quarter. I guess I was lucky. I had a small class, which is always nice. But thank you, and again, we're going to be here Tuesday, and we'll review Thursday, but I think this is kind of like the bookend here, so. All right, again, I'll be around for a little while if you have other questions. I'll stay long